Okay, really sorry guys about this. So, a couple months ago, a friend of mine posted this post on Facebook asking his friends to basically judge how fast this algorithm is written in C++. And I know it's not Ruby, so let me translate it for you so it's easier on your eyes. So the algorithm goes like this. We initialize k to 0, and then we run a loop, and we increment k by 1 until it becomes equals to n squared, and then we return that n squared. Which can actually be summarized to just this, and I don't know if there's much use for that function. So when he posted that question on Facebook, I thought that was a joke. That was just somebody trying to come up with a really clever way to code up a squared n function, and so I thought it was just a joke. I placed a big haha reaction on it and moved on to the other post in my feed. But because it was 1 a.m. at night, probably nobody else paid much attention to this post, only me. So a friend didn't let go, and he actually tagged me in a comment, and he said, no, Iryna, I'm serious. This is not a joke. I'm serious. Can you please tell me how fast this algorithm is? And I said, well, it's weird that he's serious about this, but fine. I can try to judge the complexity of this algorithm. I can comment on it. But before I could, there was another comment posted, and it said, but how do we measure the speed of the algorithm? What do we use? Do we count how many times we add things, or how many times we multiply things? Or do we also take into account how many times we compare, do the if-then comparison? Those certainly take up some of the computing time. And I wasn't sure if the guy was serious or he was joking, but it struck me that of course, this would be a valid question. This would be, in fact, the question to ask if you had never heard of the BigO notation and you wanted to approach this problem reasoning from the first principles. And so I just thought it would make a good topic for the talk. And just by the show of hands, can you raise a hand if you have heard of the BigO notation or the asymptotic complexity of algorithms? Yeah, almost everyone. Great. Do you feel like you can comfortably assess an algorithmic complexity of just any solution? Okay, so there will be something to talk about. But in my experience, even the people that have heard about the BigO notation, when they come for an interview or when they're asked a question, they have a few very common misconceptions that I want to talk about today. So, as I said, some long time ago, I don't remember, I haven't researched the historical context, but programmers sort of asked the very same question, and they wanted to come up with a way to compare different algorithms and to see which one is more efficient. But before we dive into that, let's ask ourselves a question: is this even needed? Like, do we even need to compare how fast an algorithmic solution is versus the other? Aren't computers like super fast and can do like billion operations per second? Like, do we even need to solve this problem? And how many of you have heard of the grain and the chessboard problem, or a tale? Yeah, great. So there's the tale that says there was a king long time ago and a servant, and the servant did a great favor to the king, and the king said, how can I thank you? And the servant said, well, if we take a chessboard, if you put one grain on the first square of the chessboard, and then on the second square of the chessboard, you put 2 grains, and then you just double the amount of grains on each square. And by the time you reach 64, you just give me that amount of grains that is on the chessboard, and that will be enough. I don't need much. And so if we take this problem and we take it to its 5th step, so the grain is only on 5 squares of the chessboard. So at this point, there's only, I think, 31 grains on the chessboard. But by the time you reach the 64th square, many of you might not have guessed that the amount of grains will be this number. So it's 2 to the power of 64, and it's very, very large. And we as humans, we don't really have that intuition for those large numbers, because in our everyday life, we don't operate in such a big numbers. So we tend, if we were to guess, I guess most of you, if you were to guess, you would have guessed a smaller number. Or there's in 1983, a physicist wrote in an American Journal of Physics that he has discovered that when a domino falls, it doesn't just knock another domino of the same size down. It can actually knock down a domino up to 50% larger than its original size. So, wait, I have a laser. So if we take 50% of the first domino and make the next domino as large as the first one plus 50% and line them up like this, if we knock over this first domino, it will actually trigger a chain reaction and knock down all the dominoes up to the, all the way up to the biggest one. And so if we start with a normal domino, just like the size, I don't know, like 5 centimeters or so, and we keep going in this geometrical progression, by the time we get to the 57th domino, the size of that domino will be actually the length from the Earth to the moon. So it's just 57 dominoes. So this is just to show you that some numbers, when left unattended, can get really out of hand. And so even if we have really powerful computers, if we don't watch the complexity of our algorithmic solutions, we can really get ourselves into trouble. And by the way, my talk is a lightning talk, so I couldn't fit in too many real-world examples, but if you want to talk about them afterwards, we have actually run into an asymptotic problem in our project, and it's a funny tale, and I can tell you that over a beer. So, why is the BigO notation useful, aside from giving you sort of like a framework and an intuition to think about how complex your algorithm is and how efficient it is? If you ever wanted to participate in like a programming competition like LeetCode or CodeGem from Google, this is something that's used very often in any sort of preparation material. So it's useful to sort of understand what it means. And also, if you were ever to interview for sort of these big tech companies, they often ask what's the complexity of blah, blah, blah algorithm? And I don't like those sorts of questions, but if I were to prepare for those interviews, I would have certainly dived into the details. So, so BigO notation formally is defined as f of x is in a big O g of x if and only if there exists a k and an x naught such that for any x that is greater than or equal to x naught, f of x is less than or equal to k times g of x. No, this is the real definition of BigO notation if you were to like open the Wikipedia. So it's really not friendly to mere mortals. So let me try to translate that into human language. So I think of a BigO notation as answering the question, how fast does the runtime grow in proportion to the problem size? So if we say that the problem size is displayed on the left via these red dots, and the runtime is on the right. So as we double our problem size, we go from 2 dots to 4 dots. How does the runtime increase? Does it double as well? Does it triple? Does it stay the same? Does it stay constant? So this is the only question that the BigO notation is concerned with. But to better understand this, let's first define what is the size of the problem. What do we talk about when we talk about the size of the problem? And it really depends on the task you're trying to solve. So for example, if you're trying to sort an array of numbers, the size of the problem is just the length of the array. Think of it as the larger your array, the more difficult it is to sort it, the more time it will take to sort it, usually, generally. So this is the size of your problem. If you were, say, you had to inverse a string, so put all the characters in a reverse order, well, the length of the problem would be the amount of characters in your string. So in this case, that would be 14. And then depending on the task, you're trying to find a measurement that directly affects the runtime of the solution. And that's your size of the problem. So now we go to the runtime complexity. So there's a size of the problem, and there's the complexity of the solution you're using to solve this problem. So let's say we have a problem, and we are trying to answer, we have a string of text, and we are trying to answer how many letters O are in a string of text. So if we had this piece of text that says BigO notation, and we had to write a piece of code that counts how many times a letter O is encountered in the string, we would normally have to go through every letter in the string and check if it's equal to O, uppercase or lowercase. And then if it is equal, then we increment some sort of counter, and then we return it from a function. So the size of the problem is 14, but the complexity of the solution is also 14, because we sort of perform 14 steps for this string, and on each step we perform some fixed amount of operations. We maybe check if the letter is equal to O, we may increment some counter, but for the intents and purposes of BigO notation, we don't count the amount of things we do per step, we just sort of count the number of steps. And so, of course, the intuition is the larger the string, the more steps you have to do. So in BigO notation, we write this as BigO n. So this says that if we take n, a string of length n, it takes us n steps to compute the solution to the problem. So let's say we have another task. We have to print all possible 2-digit combinations, and we write this piece of code from 0 to 9, so it's basically 2 nested loops. And because we go through the first loop 10 times, and then for each step in the first loop, we run another loop. So it's 10 multiplied by 10, or n multiplied by n, or n squared, or quadratic BigO notation. Or, for example, if we need to get an initial of a name. So we have a name, and by the way, I'm skipping here like edge case scenarios where nil was passed or something. But let's say you receive a string of text which signifies a first name, and you have to, you just have to return a first letter followed by a dot, and that's the entire purpose of this function. And can you tell me what is the complexity of this solution? Yes, correct. Because it doesn't matter how long the name is, you're just taking the first letter. You're always performing a constant amount of operations, so it's BigO on. So what if we took all of these complexities and put them on plotted them on a graph, geometry? So BigO notation says that the best complexity that we can get to is the constant complexity, this line over here. And then sort of like the next best one is log n, and then the n one. I'm skipping the square root. And then once we get beyond the BigO n into the n squared, or I think it's n to the 4th power, or to the 3rd, I can't see it. And this is the n squared n, or if we get into a factorial notation, we are really in a danger zone. We can really approach solutions that mirror the chessboard problem. So most of the complexities fall into one of these buckets. So it's constant, log n, n squared, 2 to the power of n, or n factorial. And I think the colors are not displayed very well, but basically the first two rows are color coded as green. Then this is sort of yellow, orange, and then red. So the closer to the top we are, the better the complexity, and then the closer to the bottom, like seriously, not very useful. So this is I've just covered the part that most of the people that have heard of the BigO notation sort of know about. But there's there's a few misconceptions that many people get wrong, and I've seen this many times in the interviews. So I want to cover 2 cases of complexities that you will never see normally. So you would never see like a BigO 5 of n, or BigO 13 of n squared. And why is that? While it is tempting to say that if we have an array of n numbers, and we perform n steps, and in each step we perform these 5 operations. So it's n multiplied by 5, so the complexity must be 5n. But BigO notation doesn't care about the 5. It doesn't care about any constants that can be extracted. Sorry, I don't think it works very well. That can be extracted outside of this equation. So if there's a 5 that's multiplied by n, you can just ignore the 5 and drop it. And many people don't know why that is so. And the intuition that I use for understanding it is, first I take a step back and I ask myself, why is it that we even bother with with judging how fast the algorithm is? What we want to know is, do we have enough computing capacity to solve this problem, to run this algorithm and get to a solution? So because there are certain problems, such as a traveling salesman problem, for example, where given a large amount of data, we don't really have personal computers powerful enough to solve these problems. And so let's say if you want to say that the complexity of the problem is 5n, and you have a computer that's only capable barely to perform n operations, and it cannot perform 5n operations. Well, the thinking behind this is, well, you can probably scramble and find 4 other such computers and put them together to the task and still solve this problem. So it's not a big deal. It still can be deemed as solvable. And even if you say, like, wait, but what if the entire computing capacity on the planet Earth adds up to only being able to perform n operations of your algorithm, and we cannot find enough computing power to perform 5n operations. Well, then Moore's law comes into effect, which says that the density of the transistors in the integrated circuits doubles roughly every 2 years. So even if today this problem is not solvable, let's wait another 4 years or so, we'll gain enough capacity, we'll still solve this problem. So that's why if you're tempted to say that the complexity of the algorithm is 5n, just say it's big O n. So that's the rule number one that many people get confused about. And then the other thing that you will never see is sort of complexities that are that look like a number of added polynomials. So big O n to the third plus n squared plus n, while in reality your algorithm may need some preparation work to do. So for example, you may do an algorithm where you first need to initialize an array, and that's the complexity of n, and then you have to sort of like sort it using, let's say, bubble sort, so that's the complexity of n squared, and then you actually run your algorithm on a sorted array. So you might be tempted to say that, well, the complexity of my entire solution is n to the third plus n squared plus n, but because we have settled that the computers are powerful enough to solve small problems, the only case where we really run into a problem is as we approach really large numbers. So for the sake of simplicity, let's say as we approach infinity. So as we approach infinity with n, the lower, like the less dominant terms, the less, the functions that are less sort of like rising or slower, they will begin to have less and less impact. And the only thing that will drive like the slope of that graph will be this dominant term n to the power of 3, or n to the power of 2. So if you're tempted to judge your complexity as sort of like this complex equation, just simplify it and just drop everything except for the dominant term. Now, yeah. Real world example. This is actually a simplified problem from a task that I found on Google Jam code competition, Google Code Jam competition. And it said, let's imagine we have a bunch of dancers and they're all standing in a row, in a circle, and the music is playing. And let's say each dancer has a position, so we start from 1 and we count until 12, or however many dancers there are. There could be a large amount of dancers. And the music starts playing, and to each beat of the music, the dancers dance. And the rule is like this. On the first beat of the music, the dancers switch positions, and they take 2 steps clockwise. And then on the second beat of the music, they take 1 step back, counterclockwise, and they just keep dancing like this as long as the music plays. And the question is, let's say we only care about this one dancer that's in position 1. And we say, so after a music has played for a long enough time, and the music stops, at which position will this one dancer end up that we care about? And for the sake of simplicity, let's say that the music will play for as many beats as there are the dancers. So we have n dancers, and there will be n beats of the music, so n rounds of this sort of like algorithmic dancing. And so you might be I know it doesn't seem like very much related to real life, but it is. So you might be tempted when solving this problem, yeah, like this is the dance. Oh yeah, I wanted to first sort of like assess the size of the problem. So as I said, we have n dancers and the music plays n times. Well, we could really say it's n squared or n plus n, but let's just stick to the size of the problem is n. Just how many dancers there are, that's the size of our problem. And so one way you might be tempted to solve this solution is to initialize an array. I think there's something with the, so in my presentation, there's square boxes right here, but somehow they're not displayed, but you can imagine them. I don't know, they're shown here, but they're not shown here. I'm not sure what it is. Maybe it's the contrast that's not showing. So you might be tempted to initialize an array. Yeah, and just fill the array with ID numbers of dancers, and just sort of like simulate this entire process. And you can just write a piece of code that says, n times shift the array forward 2 steps, and then backward 1 step, and then forward 2 steps, and then backward 1 step, and then when the outer loop is finished, you're just trying to find this girl and trying to see where she ended up. So in this case, what do you think the complexity will be? So we are shifting an array n times. And to shift an array, it really takes it's a complexity of n, because you shift every, so you sort of like, if you need to shift the array, you take this guy out, you shift everyone, so you do n operations, and then you put the guy back in. So it's actually n multiplied by n, or n squared. And we have seen in the table of the complexities that n squared is really not an ideal complexity. So if you were to participate in this coding competition as I was, when you thought of the solution, you might have stopped yourself and said, like, I really have to get down to maybe a linear complexity of the solution. And you might have thought, wait a minute, I don't really care about all the other dancers, so I don't care where they end up. So I don't really need this array. I don't really need to shift the array back and forth. All I can do is just sort of like track the position of one dancer. So we write a function. I should have took you up on that offer for the clicker. So we write a function that accepts our n and the initial position of the dancer that we care about. And it says dancer position initialized with the initial position. And then however many times the music plays, if the number is odd, we add 2 to the position. If the number is even, we subtract 1. So it's like sort of mimicking the 2-step clockwise, 1-step counterclockwise, 2-step clockwise, 1-step counterclockwise. And then when we are done, we sort of take the remainder of the division by a dancer's count. And what this does is, so if there's 12 dancers, if you keep adding and subtracting, adding and subtracting, you may end up with a position that says 14. Well, we only have 12 spots, so we have to like sort of divide by 12 and take the remainder of that to understand which the position the dancer is exactly in. And because in this situation, we only have one loop that sort of performs a fixed amount of operations, the complexity of this solution is actually big O n, and it's much better than big O n squared. But can we do better? How do you do better? Come again? N divided by 2. And what do we do with that?
So we just take the, like, so if this is odd, we divide by 2 and take what we got, 0 or 1.
Mm-hmm.
And in this case, like, if each second step is kind of only one step.
Yes, exactly.
If it is like 0, it means that we need to add 2. If this is 1, it will be like what we got, like n divided by 2.
Mm-hmm. Yes, exactly. You might have noticed the sort of like the formula. So when we hear the first beat of the music, we advance 2 steps, and then on the second beat we go backward 1 step. So basically, after 2 beats of music, we have only advanced 1 step. So we can actually sort of like devise a formula. I need to complement your solution with a bit of an addition. If the count of dancers is odd, we also need to add 2, because this is like the last step. The last beat, the additional beat, and then we take the remainder to normalize our dancer's position. And the complexity of this solution is actually big O1. So we went from big O n squared to big O n to big O1, and we have this table, and judging by that, we have eventually arrived at a best case scenario solution. And this is Nick laughed at the problem, and it is a very funny problem, and it seems like very far-fetched from the real-life tasks that we are doing. But come talk to me at the after party, and I can really include a lot of real-life examples where this really bit us in the ass. So this is all that the BigO really deals with, and that's all that's covered in this scary, scary mathematical formula. So do you have any questions?
Raise your hand, say your name, and then say your question, okay?
What kind of source?
Say your name.
My name is Volodya. Hi, everyone. What kind of sources I have to read to know this stuff? Except Google and
Well, actually, Googling is actually not a very useful answer because when you Google, you find this. And
books or special sources.
let me do this. Well, the thing is that I used to do competition programming when I was in high school, so I learned this 10 years ago, and it's hard for me to remember what sources I used to learn it. I should have prepared. It's an obvious question. So let me think. Let me post some links in the pivorak group afterwards.
Yeah, guys, we have pivorak community Slack account, so Ira is there, so you can ask questions. Okay, so just question. 1 second.
Okay.
Hi, my name is. 1 second.
Hi, Alex. I think I just have the answer to your question, Alex. Hi. I think the good one, explanation of algorithms and BigO problem, I think I met it in CS50. There is
Oh, right.
there is such Harvard courses. It's absolutely free. We have also, it's presented on edX platform, and also we have a Ukrainian translation.
On Prometheus. Yes.
And
So.
there they explain it quite easy for basics.
Yeah, that's a very good recommendation. CS50 by Harvard course.
One more question.
First of all, thank you for your speech and for the topic. And my question will be, so the main idea to understand the complexity is to optimize our algorithms. And like in your memory or in your biography, what algorithm was the most complex, which you make the more beneficial optimization?
Okay, I know of an algorithm. It was a very interesting problem, but I need to draw it. I'm not sure. Okay, so it was a. So it was a test. I think it was a test assignment, to pass an interview or something. And I wasn't applying for the interview. I just played with it. It was interesting. So it. Let me think if I can explain it in like a decent amount of time.
We still have 25 minutes.
So you know of a bit.ly link shortener that can shorten links into like these, I don't know, like strings like these. So you pass around an arbitrary large link and it like shortens it. And the task is to write a link shortener. But there was a couple of there were a couple of restrictions, and such that you couldn't really use a digit 0 because it is easily confused with an O. And there was a bunch of other restrictions like that, and the other one was that you were really you were to start with a 5-letter combination, and you had to really exhaust the entire amount of combinations before moving on to a 6-letter combination. So this task of how do you approach this? Do you pre-generate all of the possible combinations? Do you generate them randomly and then just check if such a task, like a string exists in the database? And so I have, like, through a series of iterations, I arrived at a solution that was both BigO1 in runtime complexity and BigO1 in memory complexity. So you can use BigO Notation to assess both the runtime complexity, how long it takes to run the algorithm, and also how much memory you need to allocate to solve the algorithm. Because it's easy to solve this with a runtime complexity of BigO1, but with a memory complexity of BigOn squared, I think. Or no, not squared. So if we have 5-letter combinations, that's how many letters we are allowed to use to the power of 5. So it's a very large memory space complexity. And then at the after party, come talk to me about the one-time codes, and I'll tell you another story.
Thanks again.